Two engineers ship the exact same feature. 6 months later, one of them dreads every minor change request, while the other ships updates in minutes. The first codebase is a tangled mess, snapping under the weight of its own complexity. 5 specific rules govern that gap, the solid principles. These 5 principles act as the grammar of maintainable, object-oriented code. Learn them once, and they quietly govern every good design decision you make from here on out. Here is the entire framework at a glance. Single responsibility. One class, one reason to change. Open-closed. Open to extension, closed to modification. Liskov substitution. Subtypes must behave like their parents. Interface segregation. Many small interfaces beat one fat one. And dependency inversion. Depend on abstractions, not concretions. Memorizing these rules is the leap that takes you from chaotic scripting to predictable, future-proof engineering. Let's unpack exactly how each one works. We start with the S, the single responsibility principle. A class must have exactly one job and exactly one reason to change. Take a look at this bloated class. It tries to calculate a mathematical report while simultaneously formatting its layout. By separating the math logic from the print formatting into 2 distinct blocks, we isolate their functions. You want your code to act like a precise surgeon's scalpel, rather than a clunky multi-tool Swiss Army knife, where pulling out one tool accidentally jams another. By isolating responsibilities, you guarantee that a simple CSS tweak to your formatting will never accidentally trigger a mathematical failure in production. Next is the open-closed principle. Software entities must be open for extension, but strictly closed for modification. When a new requirement comes in, the instinct is often to pry open code that already works perfectly. Every time you edit tested code, you risk breaking it. Instead, look at this architecture. We add new behaviors by plugging in entirely new classes through a shared slot, never forcing the main box to open. Preserving the integrity of existing code while extending its capabilities is the core objective behind almost every advanced design pattern you will ever learn. The L stands for the Liskov substitution principle. Anywhere a parent type is expected, its subtype must be able to drop in without causing errors or surprises. This diagram shows the classic trap of a square extending a rectangle. A rectangle allows width and height to be set independently. If a square inherits those independent parameters, its mathematics fatally clash, triggering an error. It lies about what it is. It is the exact real-world equivalent of ordering a decaf coffee, being served a regular one, and ending up awake at 3 a.m. The contract was broken. If a subtype cannot strictly honor the established expectations of its parent, the inheritance model is broken, and the system cannot be trusted. That brings us to the interface segregation principle. Clients should never be forced to depend on methods they do not actually use. Watch what happens to this monolithic machine interface. When it forces a basic printer to carry deadweight code for faxing and scanning, we shatter it into 3 distinct, smaller interfaces. Bundling dependencies is like being forced into an expensive 500-channel cable package when you only want a single network. It's inefficient. Implementing many small, role-specific contracts will always yield a stronger, more flexible system than forcing a single, generalized compromise. Finally, the dependency inversion principle. Both high-level policies and low-level details must rely strictly on abstractions, not concrete implementations. A common architectural flaw is writing an order service that hard-codes a direct connection to a specific vendor tool, like a Stripe client. If you want to switch to a different provider, you have to rewrite the service. This flowchart fixes it. We flip the dependency. Both the order service and the Stripe client now point toward a neutral payment gateway interface. With this inverted structure, engineers can instantly swap vendors or mock the gateway during testing without touching core logic. Inverting dependencies entirely decouples your vital business logic from the volatility of external tools and third-party APIs. That is the ultimate payoff of solid code. Changes are localized, duplication is eliminated, and you can comfortably deploy your updates on a Friday afternoon without holding your breath. Because these principles favor small, single-purpose classes and role-specific interfaces, you need a way to assemble these pieces without creating a rigid top-down hierarchy. This requires understanding the difference between an is-a relationship and a has-a relationship. On the left, classical inheritance, an is-a relationship, where a dog extends an animal. On the right, composition, a has-a relationship, where a par holds a reference to an engine. Modern architecture leans away from rigid inheritance models, relying instead on flexible composition. Scalability emerges when you combine these simple, isolated objects into a larger whole, rather than forcing them into deep, nested hierarchies. One job, extend, don't modify, substitute safely, slim interfaces, depend on abstractions. Once you see the strategy pattern as just a concrete application of dependency inversion, the magic of advanced design patterns begins to look like standard engineering. They are simply these 5 principles packaged for common problems. Try this today. Open up your current codebase and find a single class that violates just one of these principles. Fix it. Applying these 5 rules consistently transforms the nature of your work, from writing code to engineering systems that last.